let's go to operator. We have been talking about basis, right? This is the boring wave function we have talking about. It's just a state. The states, we did not do wave mechanics, we just matrix quantum mechanics. We say the state is a linear combination of basis state, alpha 0 plus beta 1. We can represent this state on a broad sphere, which we will discuss later. Now I don't want to discuss broad sphere, but here you see something. In this broad sphere, 0 and 1 are here, plus and minus are here. Right? We will explain this later, so don't worry. The reason I want to point this out is that every vector can be, every one qubit vector can be represented as one point on this broad sphere. So trust me for now. We don't need to go too deep. The reason I show this is just that now you have a point here. Then if you transform one point to another point, let's say you apply a quantum gate, isn't that it's like moving this point to another point on the broad sphere? Right? If you accept, you agree, you trust me that every point is represented on the surface of this sphere, on the surface of the Earth. Then I change the state. I must be moving this thing from San Francisco to San Diego, for example. So conceptually, it's just a rotation of vector when you apply a quantum gate. We call this operation, right? So you have learned before, how do you change a vector in matrix? Yeah. What do you do to change a vector? I mean, to rotate a vector. Do you remember? Matrix multiplication. Very good. Matrix, right? So for any vector for any vector V, we multiply this by a matrix. Then I will get another vector. And if this vector is somewhere here, this is U. Isn't that this is just I rotate this vector from here to here using M, using matrix M. So that's the only concept I want you to know. A vector is a column of numbers. You multiply by the matrix, it becomes another column of numbers, which represent another vector. So rotate a vector is just like this, right? And that is the main point of this line. That's it, okay? So let's do an example. For example, here, what is V, by the way? For what I wrote, for what I put here, what is V in the 0 and 1 basis? What is V? One zero, very good, just 0. Or, as someone say, just 1 times 0. So what is in column form? 1 0, because I have 1 part of 0 and 0 part of 1. Right? Again, you get confused why what 0 is here, 1 is here. We discuss later. You just trust me, I put it correct. Okay? Yeah, this broad sphere can be very confusing, but for now, just trust me. Now, I tell you something you are going to learn later. I apply a matrix M, which I call it H, equals to 1 over square root 2, 1, 1, 1, negative 1. That's it. I give you. You don't know what it is. It's a matrix. It's a valid matrix to represent a rotation of the vector on the broad sphere. Let's try to see what it is. So M operates on V equals to H operates on V equal to 1 over square root 2, 1, 1, 1, negative 1 times 1, 0. Do you agree? Take a look at this one. I'm just substituting H by this and V equal to 1, 0, right? If you do matrix multiplication, what do you get for this one? Someone? Should be a very simple multiplication. You get row times column becomes the first element. Row times column becomes the second element, right? So what is this? Let me spell it out. 1 times 1 plus 1 times 0, right? 1 times 1 plus negative 1 times 0, which is equal to 1 over square root 2, 1, 1, which is equals to 1 over square root 2, 0 plus 1, which is equals to 1 over square, no, what is this? You forgot. What is 1 over square root 2, 0 plus 1? Plus, right? Not for this figure, however, right? I just say they have the same relationship, but not for this figure. This just equal to plus. So basically, what I have done is that I apply this H matrix and I rotate this one to plus state. Okay, so this is just an initial feeling. The main thing is that you operate the vector by matrix multiplication. So the operator or any pulse is corresponding to a matrix. A matrix will rotate a vector about this broad sphere. And these are the basic matrix multiplication you really need to learn. You need to be very familiar with this. Right? Although you can use Python or whatever to do it, but basic thing you need to learn. Any questions? But you don't worry about how I label this. We will learn this later, right? No need to worry about why H is so special. This is the so-called Hadamard gate. With this, we can really go to a little bit more, as I mentioned earlier. A quantum gate is just an operator. Basically, eventually you come up with a matrix. Yeah, a lot of physics, you keep deriving, finding the Hamiltonian, solving Schrödinger equation, eventually you get a matrix. Apply this matrix, you want to psi, you rotate it, rotate it, rotate it. Okay? The most basic gate, and also the most basic matrix, of course, is the identity gate. How do you implement identity gate? They say identity gate, actually. Yes, but physically, how do you implement? Yeah, how do you multiply by identity matrix? Yeah, just don't do anything. I know this is tricking you, right? But this is very important. So in quantum circuit, sometimes you see identity gate, but it means that don't do anything. But still, we need to know the math, right? I equals to 1001, like what you said, right? So why? Let me show you. I times any vector v equals to 1001 times alpha beta equals to, let's try the math again, 1 times alpha plus 0 times beta, 0 times alpha plus 1 times beta, which is equal to alpha beta, which is equal to V. We often try to prove something that is identity by showing that the matrix times V equals to itself, times any V equal to itself, if V is not a zero vector. Okay? So very simple, right? Done. But we learned the basics. The second gate we want to learn is the NOT gate. Now, here I did not say is that, how do we define a gate? We actually define a gate. This is important. You need to memorize this. Each gate is defined by how it rotates the basis state. If we know how it rotates each basis state, x0, x1, xn. But for one qubit is what? 0 and 1. If I know how 0 and 1 going to rotate, I define a gate. Okay? For example, NOT gate. NOT gate, sometimes we call it X gate, just some names, or the symbol is name. This is the definition. As I said earlier, you define by how you rotate the gate. X applied to 0 give you 1. X applied to 1 give you 0. This is definition, no argument, right? Because of this definition, then I can say that I can represent X as 0, 1, 1, 0, because this will do the work, do the job. Why? For example, X applied to 0. X is 0, 1, 1, 0, right? What is 0 in the column form again? 1, 0. Thank you. Yeah. I did not say it, but I gradually established a convention in this class. And this convention is also used often by others, is that I put 0 as the first row and 1 as the second row. You do the matrix multiplication, what do you get? I won't go to details, just, 0, and then 1. What is 0, 1 in CAD notation? 1, right? So you see that it does flip the gates from bases from 0 to 1 and 1 to 0, right? In general, right, I would just, if I have psi equals to alpha 0 plus beta 1, which is equal to alpha beta, I have two ways to do this. I say X apply to psi. Because this is superposition, quantum mechanics is linear. I can say this is equal to alpha x on 0 plus beta x on 1. Are you okay with what I'm saying? I remember that X is a matrix. This is a vector. So I apply to here, I can just apply to the individual matrix, right? And by the definition, what is X? 0. 1. What is beta 1? I mean, what is x1? Sorry. 0. Right? And that is exactly, or if I want to write better, I can put beta 0 plus alpha 1. Okay? So you can say I swap the coefficient. Now maybe to save time, and maybe I just do it. Or if I use the matrix to do it, I do it a little bit faster. It's just 0, 1, 1, 0 times alpha beta. Of course, you will get beta alpha. And they are the same. Right? So there are two ways to do this. Either just look at this symbol, look at definition. We often need this. In simulation, we use matrix. Right? Any questions? Any questions? Is that clear? Let's keep practicing. Another important gate is the phase shift gate, right? Before that, let's just review something. It's e to the power I phi. Good. Cos phi plus I psi phi. Okay? And this one is called the phase. Now, this one you need to review, or you forgot. If not, again, you just need to trust me and use it, right? If you don't have time, because we have more important topic. But after all, you learned that before. All you need to do just have a cheat sheet. Remember, e to the I phi is cos phi plus I sin phi. Because if you remember this complex plane, right, this is real, this is imaginary. If you point here, this is phi, and this is e to the power I phi, if the length is 1 for the unit circle. Right, and you find that this is cosine phi plus I sin phi. Okay, so you can do a review. If not, just trust me. Okay, this is the phase. Now, what we are going to define a phase shift gauge, which is very important. And for not just review, really just spend some time to understand, because phase is very important in quantum computing. Right, so review this basic. We call this phase shift gate, I call it PS phase shift, and then comma phi means that the gate will shift the phase by an angle phi. Okay, so what does it do? If it is applied to 0, do nothing. But if it is applied to 1, you will add e to power I phi in front of 1. This is the definition. Accept it. Okay, and we are defining by how it rotates the basis state as we have promised. If this is the case, you definitely will find that I can represent this phase shift gate by this matrix 1, 0, 0, e to the power I phi. It's just like the identity gate, except that this one becomes e to the power I phi. Let's digest a little bit. Any questions? So assume you are okay, then just stop me if you have questions, right? Let's just understand what it is doing, right? Let's first check if this is correct actually. E phase shift gate apply to 1. What is this? 1, 0, 0, e I phi. Again, what is 1? 0, 1. Correct? Everyone agree? 1 is 0, 1, right? So you do the multiplication, what you get? What is the top element? 0, correct? And what's the bottom element? Either I phi, right? Let me write it one more time. I can write it as this. Is this valid? I factorize it. Because all I need to do is just multiply this by 0 is still 0, this by 1 is this one, so it's valid. I do a factorization. Just a factorization for a vector, right, for a matrix. And what is this? In cat form? 1. This is exactly what we just defined. So when I apply to 1, it adds a phase to it. We say we add a phase to it by phi, an additional phase. Phi. Okay? So then in general, if I apply it to a general vector, UPS phi, applied to alpha beta, is equal to 1, 0, 0, EI phi. This time, an alpha beta. Let me spell out how to do that. 1 times alpha plus 0 times beta. 0 times alpha plus EI phi times beta, right? So I hope that you are you all know how to do matrix multiplication, but in the last term, I saw some student kind of mess up and then you get the wrong answer, right? So be very careful. This is the basic thing. And this gives us what? Alpha E plus I phi beta. Okay? And if I write it in the bracket form, it is alpha 0 plus e to the I phi beta 1. So you see that I don't change the phase of 0, but I change the phase of beta. This is important. You give a relative phase change to this state, and then it's not the same state. This is very important. A relative, if you change them at the same time later, I will tell you that this is a global phase change. It doesn't matter. But we will talk about that later. But for this one, they relatively change. So it's completely different from the original state. Okay, any questions about this? I do want to ask you one thing. What is the probability of measure 1 after this gate? What is the probability of measure 1 now? What is that? Can you do it by definition? How do you find the probability of measuring 1? What is that? EI phi and is it only EI phi? Beta. Yeah, you missed this one. Very good. Very good. Yeah, you're all right, but sometimes too fast. Complex conjugate of it times I phi beta, right? Because just take it the whole thing. We're saying that because now the coefficient in front of 1 is this whole thing. This is a complex number. You need to do the whole thing by definition. Right? So complex conjugate times this, right? What is the complex conjugate of EI phi? E minus I phi. Yeah, very good. E minus I phi, right? If you are not sure, look at this definition. I put negative in front of the imaginary part, right? Then it becomes plus I sine negative phi. Cosine negative phi is cosine phi. So yeah, so this is E negative I phi. Go back to make sure that you understand this, right? Times I phi, because I do have I phi here, right? And then times what? Beta star beta. What is E negative phi times E negative I phi times E I phi? 1, right? So this is still equal to beta squared. So here, show you again, the phase change does not change the probability. But it's very important, it does change the state. From measurement perspective, from our classical perspective, we cannot distinguish whether it has a phase change or not, unless we try to use it to do some interference with other qubit. By this qubit itself, you actually don't know what happened to it. You just keep measuring, you still get the same probability. That's a very important concept. Okay? So this is phase shift gate. This is a general phase shift gate. There are some special phase shift gate you will see very often. The first one, phase shift gate with phi equal to pi. So what is that? 1, 0, 0, e to the power I pi. Again, this is just like e to the power I pi. I only do it one time. Go back to do it yourself. Cosine pi plus I sine pi, right? What is sine pi, by the way? What is sine 180 degrees? 0. What is cosine pi? -1. You did not realize that you need to use this again after 10 years of study, right? So this is equal to 1, 0, 0, -1. This is something we call Z gate. You will use a lot. We are going to implement Z gate as our first gate. Okay? Now you also have this one with phi equal to pi over 2. So you go back and actually I don't have the, we don't need to put the number. This is called S gate. Okay? You also have phi equal to pi over 4. This is called T gate. Now there's some confusion. It's also called pi over 8 gate. Right? Although it's pi over 4, but it's called pi over 8 gate. That is because we will factorize this out. This is equals to e to the power I over pi over 8 times e to the power negative I pi over 8, 0, 0, e to the power I pi over 8. When you make this symmetric, then it's pi over 8. So it's okay. We're not testing you this. This is just for you in the future to read books or paper. You understand what happened. All I need you to know here is just that you can substitute this. And Z, ST are some very important gates. Okay, and by the way, I would like to mention that T squared, which is T times T, you apply 2T gate is equal to applying 1S gate. S squared, which is S times S, remember they are matrix, is just equal to Z gate. Okay? So now I want to draw your attention. Last time I said that a universal set of quantum gate can be formed by H, S, T, and control knot. Here I show you that ST, what a ST. And H we already just mentioned, Hadamard gate earlier. I will mention again. But is this okay? So although a lot of math, but we try to define the gates by how it changed the basis state. That is the fundamental thing. Memorize this. Every time you got lost, just say, okay, how it changed the basis state. Phase shift gate change the basis state by keeping 0 as it is, by adding a phase to 1. And you have a general form of this. And then you can put in any angle. Then you get some special gate. That's it, okay? Hadamard gates, we have learned Hadamard gate just now. But let's see what it does, right? I think I can only finish this today. So I will just stop at this slide, right? We define Hadamard gate as, if applied to 0, it gives me 1 over square root 2, 0 plus 1. Basically, it's easy to memorize. It becomes a superposition. You give me a basis state 0, it becomes the superposition of two basis states, 0 and 1. Any idea why it ends up with 1 over square root 2? Of course, there is definition, right? But why they define it as 1 over square root 2? Why don't you just 0 plus 1?
Probabilities of the same.
Very good probability, and then what? Normalization, equivalent, right? What they're saying. He said probability needs to sum to 1, means this vector need to be normalized, right? The length need to be 1. You try to do it. If you don't have 1 over square root 2, what is the total length? 1 plus 1, right? Which is 2. Okay, very good. So, and we also define it as, if I apply to 1, I will get 1 over square root 2, 0 minus 1, right? This is definition, and we showed this earlier. So because of that, you can check. This one should have a matrix form of 1, 1, 1, negative 1. Interestingly, this is also the 1-qubit quantum Fourier transform. Later, we will not talk about this, but it's 1-qubit quantum Fourier transform will give you this. Right? How do you, I mean, if you don't have any other thing important, then just memorize it, right? So, but I do want to say one thing. We earlier defined also what? This is equal to plus. We define this is equal to minus. We already defined that. Okay, so if I have a Hadamard gate applied to a general state, what will I do? Yeah, of course you can say, okay, this is equals to alpha h applied to 0 plus beta h applied to 1, and then you substitute 0 as this. I mean, as h0 as this whole thing, and then 1 as this whole thing, right? But you also should be very familiar with the fact that I can say that this is equal to alpha plus times beta minus. So now, sometimes in the quantum algorithm, you might want to have two bases at the same time. That can help you understand it better, right? But luckily, in our class, this is hardware. We don't need to deal with this much. And this is the Hadamard gate. I still have 3 minutes, but I think it is better to wait for this tensor product next time, right? Any questions? Let's discuss more. Or you feel free to leave. Yeah.
Sir,
You say this is look like a phase shift gate?
no,
Okay, say again.
so if you like block the get faded.
You mean that no phases for 1 and then have a phase shift for 0?
Yeah.
Yeah. Yes. So this is a good question, right? So I'm going to erase it so not to confuse people. You find that this one, I can also put it as e to the power negative I phi times e to the power I phi 0, 0, 1. Do you agree? Because this multiply this equal to 1. This multiplies equal to, oh no, should be plus, right? So this should be plus, and then this should be minus. First of all, do you agree this one equal to this? When a number multiply matrix, you multiply the number to every element, right? So this equal to this, right? This one achieve what you said. This will only shift 0, and it won't shift 1, right? Then how about this, you say? You still have this extra, isn't that the same? But for a gate, when you multiply to here, it's just like you multiply a global phase to the state you apply to. So because if you multiply the global phase to a state you apply to, you actually cannot distinguish it. We will discuss this later, because when you do any measurement, this will get cancelled. Right? So so what I'm trying to say that you can come up with this gate, so I can even erase this and claim this is a new gate, but its physical effect is the same as this phase shift gate. So this is just a standard form. You can do anything, but they are equivalent eventually. Good question. So I'm going to erase this so that, when you study, you don't have confusion. Any other questions? It's 45 already, yeah. Okay, thank you.